Modern fighter jets are some of the most aerodynamically complex machines ever built. They operate at extreme speeds, extreme angles of attack, and under conditions where airflow behaves in highly unpredictable ways. Designing an aircraft like this purely through physical testing would be incredibly expensive, slow, and limited. This is where Computational Fluid Dynamics, or CFD for short, plays a crucial role. In this video, I'll explain what CFD is, how it works, and how it was used to optimize what was one of the most successful fighter jets ever built. Drum roll please, Dad. The Lockheed F16 Fighting Falcon. The F16 was developed in the 1970s, during a period when CFD was becoming increasingly practical in aerospace design. As a result, the F16 became one of the first fighter jets to significantly benefit from computational aerodynamic analysis. Aerodynamics is the study of how air moves around objects, and for a fighter jet like the F16, this directly affects factors such as lift, drag, stability, and maneuverability. Unlike commercial aircrafts, which are designed to be naturally stable, the F-16 prioritizes, and I mean heavily prioritizes, agility. This means they often fly at high angles of attack, where the aircraft's nose is pointed significantly above the direction of travel, as you could have seen in this image. At these angles, airflow can separate from the wing surface, leading to a loss of lift. The F-16 also operates near transonic speeds, where parts of the airflow locally exceed the speed of sound, forming shock waves that increase drag and reduce control effectiveness. The effect of these shock waves can be said to be shocking. Sorry, I apologize. That was poor. Designing an aircraft to perform well in these conditions required a deep understanding of complex airflow, an ideal application for CFD. I've said the term CFD a lot now, but what actually does CFD do? At its core, CFD predicts how fluids, such as air, move by solving the Navier-Stokes equations, a set of partial differential equations which express how the velocity, pressure, temperature, and density relate in a viscous moving fluid. These equations have never fully been solved, and you can see why. This looks utterly impossible. These equations describe conservation of mass, momentum, and energy. In simple terms, they track how air flows, accelerates, and transfers forces. Because these equations cannot be solved exactly for real aircraft shapes, CFD has to use numerical methods, meaning the equations are approximated and solved using computers. This is what allows engineers to analyze airflow around complex geometries like fighter jets. The first key step in CFD is discretization. This means that dividing the air around the aircraft into a large number of small regions called cells or control volumes. Together, these form a mesh. The mesh is much finer near the aircraft surface, especially around the wings and leading edges, where airflow changes more rapidly. This works by a principle that using more cells improves the accuracy. However, you also increase computational cost as a result. So engineers have to find the perfect balance. Most aerospace CFD use the finite volume method, or FVM, as their method of calculation. In this approach, the Navier-Stokes equations are applied to each control volume individually. Instead of focusing on what happens at a single point, FVM looks at how much mass, momentum, and energy enter and leave each cell. These transfers are called fluxes. Using Gauss's divergence theorem, volume equations are converted into surface equations, allowing engineers to track exactly what crosses each cell face. This guarantees conservation, because whatever leaves one cell has to enter another. At fighter jet speeds, airflow is almost always turbulent, meaning it contains chaotic swirling motion. Directly simulating turbulence would be far too computationally expensive. In fact, it would take so long that the aircraft would even be retired before the answer came back. So CFD usually solves the Reynolds averaged Navier-Stokes equations, or RAND. RAND equations model the average effect of turbulence rather than every tiny fluctuation. To close these equations, turbulence models such as Spalart-Alamans are used to estimate how turbulence affects the flow. Once the equations are set up for every cell, the computer solves them iteratively, repeatedly refining the solution over and over again until it converges. The final result provides detailed flow data for every cell, including pressure, velocity, and turbulence. These results are visualized using pressure contours, streamlines, and velocity maps, making complex airflow patterns easy to interpret. I say easy, but this still looks incredibly complex to me. One of the primary uses of CFD in the F-16's design was analyzing pressure distribution across the wings. CFD simulations allowed engineers to see exactly where low pressure regions formed on the upper wing surface, which are responsible for generating lift. By adjusting the wing geometry and leading edge shape in their designs, engineers were able to settle on a design which had strong lift even at high angles of attack. This directly improved the aircraft's turning performance and combat agility. CFD also helped identify regions where airflow separated early, allowing designers to modify the shape to delay the stall and improve controllability. One of the most distinctive aerodynamic features of the F-16 is its leading edge strakes, located near the wing roots. At high angles of attack, these strakes generate strong, swirling airflow structures called vortices. These vortices increase airspeed over the wings, reducing pressure and effectively increasing lift. CFD allowed engineers to visualize these vortices in data, including their strength, position, and exactly where they broke down. Because of this, they were able to optimize the strake geometry, and engineers ensured that these vortices could remain stable over the wing for longer, improving lift and maintaining control during extreme maneuvers such as dogfighting. CFD was also used to reduce drag, particularly at transonic speeds. Simulations revealed where shock waves formed on the wings and fuselage, and how they interacted with the boundary layer, the thin layer of air near the aircraft's surface. By refining the aircraft's shape, especially at the wing-fuselage junction, engineers reduced wave drag, improving acceleration, top speed, and fuel efficiency. Even small reductions in drag can significantly enhance a fighter jet's operational performance, so this was incredibly important for them. The F-16 was additionally one of the first fighter jets designed with relaxed static stability, meaning it is naturally unstable in pitch, which you may think is a silly idea. This instability, however, improves maneuverability, but would be impossible for a human pilot to control directly. So, why did they do this? Well, CFD was used to analyze how aerodynamic forces and moments changed with angle of attack and control surface deflection. This data was essential for designing the revolutionary F-16 fly-by-wire system, which automatically makes thousands of control corrections per second. The combination of CFD and digital control systems have now allowed the F-16 to safely exploit its unstable but highly agile design. So, in conclusion, computational fluid dynamics transformed how fighter jets like the F-16 were designed. By allowing engineers to visualize and optimize airflow in detail, CFD enabled performance improvements that would have been difficult to impossible by using physical testing alone. Today, CFD is even more advanced, using high-performance computing and artificial intelligence to design aircrafts such as the F-35 and future sixth-generation fighters. The F-16 stands as a milestone in aerospace engineering, demonstrating how computational methods can directly shape real-world aircraft performance. Thank you for listening, and I hope you've enjoyed.